Welcome you all to this course on electron diffraction and imaging. In the next few classes, we will discuss phase contrast microscopy. Okay. So far, what you have studied is essentially a conventional electron microscope where we can get bright field and dark field images. Okay. Different types of diffraction like parallel diffraction, Kikuchi diffraction, convergent beam diffraction. Their applications, that is what we have studied. Now we will look at what is phase contrast microscopy and what are its applications. Even in optical microscope you have studied the various types of contrast. One of the principal contrast which is used to look at biological samples where that inherently the contrast is weak, we call it as the phase contrast microscopy. What is the principle of a phase contrast microscopy? That is the light wave which enters, okay, which is scattered from the sample, which is the probe which is falling onto the sample, we can consider it as a wave. Okay. That is an electromagnetic radiation. If you consider it as a wave, there are two ways in which we can represent it. One, the graphical representation of it as a function of time or as a function of the distance, how the amplitude of the wave changes, this we can plot it. Okay. That is one. The same thing can be represented in an equation form where psi equals a into sin kx, where k equals 1 by lambda. The same thing can be written in the form of exponential, that is e to the power of I 2 pi kx. When a wave of radiation falls onto a sample, okay, suppose we assume that this is that sample, the radiation is falling on that sample, and the radiation which comes out, okay, the radiation which comes out without any interaction and some part of it which interacts with it. When an interaction takes place and there is a change, what is essentially happening, we assume that if absorption is not taking place, the only change which can take is that phase of the wave can be changed, can only change. If the phase of the wave changes, then we can write that is this is corresponding to this is the initial wave which is represented 2 corresponding to this particular wave, okay, and the one corresponding to a wave which is scattered, and the scattered wave we can A into, since it is sin theta, this theta plus 5 is the phase which has been, it could be a lag or a lead, okay, the same thing which is being written. This expression, if we now try to expand it, we can write it in this form, okay. And similarly here also this can be sin 1 equals, that is, this is just the trigonometric function which we use, sin theta plus phi equals sin theta cos phi plus cos theta sin phi. If the phase lag is, phase is very small, the change which is taking place, then this can be written as sin theta, because cos phi becomes 1 and this becomes sin phi becomes phi into cos theta. Okay. This is what essentially that amplitude becomes. This is what expression which has been derived. Okay. The same thing if we write it in the exponential form, this turns out to be to 1 plus I phi. Okay. In this one, if we look at it essentially, this can be looked at in a different way. What is this cos theta? Cos theta can be represented sin pi by 2 plus theta, which we can write it. So, that means that essentially the total wave in the wave which is the scattered wave can be considered as 1 a sin theta, which corresponds to an initial wave, plus a into phi becomes that amplitude, this is of the wave, which is essentially shifted by 90 degree with respect to this initial wave. So, then this is how this wave is going to be, okay. That is what essentially it is being written, okay, both in the exponential form or just using a periodic function sin theta. But what is essentially which we have to see it is that what is the intensity? Intensity is psi star. When we take the intensity psi star, okay, essentially what it will happen is that nothing but when we take this, the phase will vanish and only the amplitude factor comes. So, we do not get any information about the phase, as such like this. Okay. If to the scattered wave, okay, if we can introduce another phase pi by 2, either it is a lag or some, then what is essentially is going to happen is that this will give rise to, that is what suppose we introduce a phase of minus pi by 2, this will give rise to finally that psi 2, that amplitude becomes, because this wave which was initially which was like this, it has been shifted, okay, that it becomes 1 plus 5 into a sin phi. That means that whatever is the phase which has been introduced due to interaction of the beam with the sample, that has been transformed into an amplitude variation. And amplitude variation is the one which we normally see in the image as a contrast variation, when the amplitude varies from region to region. Okay. That is what essentially is the principle of phase contrast. If we introduce phase pi by 2, okay, it's a lag, it's okay, it's not a lag, it's going forward, then what's going to happen is that psi dash becomes, this is what essentially it becomes. So in both the cases we find that the variation in phase, okay, has been changed into how this phase difference could be introduced. This is done in the case of an optical microscopy, okay, by introducing what is called as a quarter wave plate. Okay. Essentially what a quarter wave plate does is, this is the one which is corresponding to a scattered radiation, this is corresponding to the direct radiation. Okay. This radiation which has undergone scattering, or we call it as a diffraction, to this, okay, by introducing a quarter wave plate, to this wave alone we introduce another pi by 2 is the phase shift. This way we can convert the phase difference which has come in as a result of scattering into an amplitude difference. So this amplitude change is directly proportional to phi. Okay. So this is how it is done in the case of an optical microscope. Now the next question comes is that how is this phase to amplitude change achieved in TEM? That is the next question which we have to address. Okay. Before we go into this one, let us look at how an image is formed in an electron microscope or in an optical microscope. It does not matter whichever is the microscope is. What we have is an object in which light is scattered from every point in different directions. These rays which are scattered in different directions, they are focused. Okay. There are two planes which we can define for a lens. One is called as a backfocal plane, another we define as that image plane. What is the diffraction plane? The rays which are scattered from different regions of the sample, but in the same direction. Here we have taken two extreme ends, the ray which is scattered in this direction and the ray which is scattered in this direction. It is focused at this point. There and the direct transmitted ray, okay, which has not undergone any diffraction from this region, they are focused at this point. The ray which are scattered in this direction, they are focused at this point. So the backfocal plane is the one in which the rays which are parallel to each other and close to the optic axis, they are brought back to a focus. What is the image plane? Image plane is the one in which the ray which are starting from different points on that sample, you see that from this point the ray is scattered in this direction, it is scattered in this direction, all these rays are brought to a focus at a particular point along the optic axis, perpendicular to optic axis in a plane. This plane we call it as the image plane. So depending upon the magnification of the lens, okay, we can get a magnified view of the object, and depending upon the resolution, okay, we will be able to resolve the features of the object. Okay. So what is the resolution? The resolution, the Rayleigh criterion says that the resolution essentially R is essentially proportional to lambda. Lambda is where the wavelength of the radiation which we are using it. Okay. In the case of an electron microscope, when the electrons are accelerated to very high energy, where it is of the order of voltages which are applied are 100 kV to 400 kV. Okay. Then the wavelength, if we consider lambda, it is for 100 kV, it is about something like 0.038 Armstrong, and it is 200 kV, lambda equals 0.025 Armstrong, or this is equal to 0.0025 nanometer. So, that means that in principle the limit of resolution is essentially corresponding to the wavelength of the radiation. Separation between atoms in all real samples is much larger than this value, correct? So, because of this, okay, if the lenses do not introduce any aberration, that means that for a point object we are able to form a point image where we assume that it is an ideal lens, it has no aberrations, or we assume that all the aberrations have been corrected and it is made into a perfect lens. In such a case, okay, for a point object we will be able to make a point image, and the resolution essentially is given by the wavelength of this radiation. That means that in principle the atom should be resolved. Okay. This you can see it especially you might have seen in the case of an optical microscope. In the case of an optical microscope when the object is a grating, or it is like if you can take a cloth which has lots of lines are there, network of a grid, if we take it, okay. Since the wavelength of the radiation is, if the grid separation is of the order of about maybe 1 micron, okay. And since we know the wavelength of the radiation is about 500 nanometers, then we will be able to see the image which is of the grid could be formed. Similarly, in this case, where in the case of crystalline materials where the atoms separation is of the order of about 1 to 2 Armstrong, in such cases since the wavelength is very small, we should be able to form in principle for a perfect lens high resolution image or an atomic image we should be able to form. This is what it becomes obvious from this transparency. Okay. Now, let us just go into little bit more detail. Okay. How do we form an image? Okay. To derive some mathematical expressions which we can use it. Okay. When we have a thin specimen which is there where the incident electron beam is there, okay. This is the direct beam and this gives rise to a direct spot, and the diffracted spots give rise to spots which are indexed as G1, G2, and these diffraction spots are arising because of the periodicity in the sample. Okay. Let us look at what will be the amplitude of the each of these diffraction spots. Okay. The incident wave we represent it as a plane wave, and it is given by the expression psi equals e to the power of I 2 pi kr. Okay. Corresponding to this particular position, what is the contribution to the amplitude from an atom at a position r, m and p, okay, is given by this expression where Fg is corresponding to the atomic scattering factor. This is especially this term comes because from a point source when it is scattering into a spherical one, okay, the amplitude at any distance r will be e to the power of I 2 pi kr by r. This you know that. Okay. Then e to the power of 2 pi g dot r, m and p is what it is going to determine the phase factor. Okay. If from all the atoms which are there which are being r, the incident beam is illuminating some volume of that sample. If we take the contribution from all of them together, psi m and p, that this is going to give the amplitude of the each of these spots. Okay. What is essentially important here is that this factor is going to change depending upon in which direction the atomic scattering is taking place, correct. This can be rewritten in a different form, which is what essentially is being done, okay, where we can introduce the term psi g, which is that extinction distance, which we will forget it for a moment. Okay. And now what I have done is that in this transparency, if you look at it, it is we can represent the k vectors corresponding to different scattered direction in this particular way, k0, k1 g1, okay, k1 g2, which corresponding to the diffraction spot g2. What is the magnitude of all these k0 equals kg1, magnitude of them, that is the vector equals 1 by lambda, which we know. Okay. But in a vector notation, if you try to write it, this kg1 will be k0 plus g1, k2 will be k0 plus g2. Okay. So, these are all the, if at any point on that image plane, what is going to be the total amplitude of the wave there, it is corresponding to the one which is coming from the transmitted region and the one coming from each of that spot. Okay. These amplitudes have to be added together. Here what is being taken is that this itself can be written as corresponding to from particular atom to various contribution. If we take it, then the psi total will be corresponding to the part of the amplitude phi 0 m and p, okay, into the term that is from here at a distance r, it is going to be there. Here this vector has to change because this will become k0 plus g, because this is the, so this is the way it will be. So, if we take sum of each of this gives rise to at each point, okay, from an atom at m and p, what is going to be the contribution which is going to be there in that image, that amplitude of that image. Okay. The same thing we can write it, okay, at what is going to be the amplitude at every point, okay, from taking each of this diffracted beam. That is what we are essentially doing, it is that we are taking each of the diffracted beam has an amplitude corresponding to it, okay, at any particular point. That is what we are trying to do is essentially, this is transmitted beam, okay, 0, this is a diffracted beam. Suppose at any particular point, okay, this is the vector k, this is another vector k1, you can assume k2. So, these two vectors at these points, when they come and join together, the total amplitude at this particular point will be corresponding to one which is coming from here and another from here. That is what essentially it is being, this is for only two beams. If we take all the beams together, this is what it has to be added together. This is the sort of an expression happens. In this, if we substitute k0, this is what essentially it will become. Now, immediately you can make out, if you see this expression, is that the periodicity of the lattice appears in these factors. Okay. Essentially what we have done it is that the wave which is a direct wave and the wave which has been scattered, we have just added together. Okay. That is essentially what is being done. So, in the case where we consider only two waves, that is which is called as a two beam condition, that is though in the diffraction spot many spots will be appearing, we are only considering one diffracted one incident beam and one diffracted beam, then this is how the expression will turn out to be. Okay. The interference of these two waves will give rise to some fringe pattern, okay, or a beat pattern which will be generated. This is what we are looking at it. In this case, what we have done, the assumption which we have made is that the lens has not introduced any aberration in the beam. Okay. So, then we can write this Kd, the diffracted beam, equals K0 plus G plus Sg is the deviation from the Bragg condition. Okay. Now, this turns out to be, if you do these substitutions, okay, this amplitude phi 0 we can write it as A, that phi g from the dynamical theory, this is the sort of an expression which has been derived. Okay. Then we can write this as phi g can be written as B into the B is going to be pi t by psi g into this term, okay, I into this one, this is what essentially written in the form of a delta. So, if we substitute this, okay, now what is essentially is going to happen is that this is the way the expression which will turn out to be to A plus B into exponential I. This, what is the intensity? Intensity is that we have got an expression for psi t. Okay. Now, we can find out psi t star because this is a complex function. Intensity I equals psi t into psi t star, that is what essentially which has been done. And when you do the algebra, this turns out to be 2 phi become A squared plus B squared plus 2AB into cos 2 pi g dash dot r plus delta. This delta what we have derived, we can substitute it, and then finally this expression turns out to be minus 2AB sin 2 pi g dash dot. Okay. Let us take the case S equals 0. Okay. That means that the diffracted beam satisfies, okay, the perfect Bragg condition. In that case, this is how the expression will turn out to be. Now, we can make out that the intensity is going to fluctuate, okay, as a function of g. Okay. How the g is there, this is going to determine the periodicity in the intensity, okay, or the intensity of the image fluctuates with the periodicity that which is g, it is going to be, that is equal to d equals 1 by modulus of g. Okay. This is what that intensity is. Okay. Now, we can just see how exactly it is implemented. That is, from this expression what we can make out is that as a function of g, the intensity is going to vary periodically. Okay. Let us look at how it is being implemented in the microscope. Okay. We have a incident spot and a diffracted spot. Okay. If we put an aperture around it, you remember that how images are formed, that ray diagram for image formation, in which at the back focal plane we put an aperture so that the image due to both of them are allowed to interfere. When the images due to this interfere, this interference will give rise to a fringe contrast, and this is how the fringe contrast turns out to be. If you look at the separation between this separation corresponds to d, okay, the lattice spacing. Okay. Depending upon the type of aperture which we use, we can use as many beams as possible to contribute to this image. In this particular case, since it is a 2 beam condition which is considered, okay, only one type of a fringe takes place, and another important factor which becomes is that the fringe spacing, if you look at it, is in the direction of g, because that it is varying in this, the contrast is varying in the direction of g. Okay. Suppose S is not equal to 0, okay, but what happens is that in such a case, in this expression, if you look at it, this term is also going to be there. Essentially what is going to happen is that this is not going to affect the fringe spacing, but what is essentially is going to happen is that depending on magnitude of S and D, okay, the fringes can shift a little bit from region to region depending upon what is the variation. This sort of deviation can occur, that is, the deviation in S can occur because even if the sample is aligned, that is, we have diffraction spots are there. Okay. It is Yavol sphere passes right through the diffraction spot. In spite of it, okay, the region to region defects could be there, which could give rise to a local change in the deviation from the Bragg condition, or the sample itself is bent a little bit, because of which also the deviation from the Bragg angle need not be 0 everywhere on the image. But this variation is not going to make some shifts in the fringe, but it does not affect the periodicity much. That is what one should remember. Okay. This is a typical high resolution lattice fringe image, which is taken from a zirconium 1 niobium using a 2 beam condition. Okay. By measuring this fringe spacing, we that is this should correspond to the lattice spacing. Okay. If you know the magnification, we can find out. Okay. Suppose we take many spots to form the diffraction. That is the case which is being considered here. Okay. Due to G1, that is another G2, G3. In such a case, what is happening, corresponding to this, perpendicular to this, we will be getting a fringe spacing. Perpendicular to this G vector, we are going to get another fringe spacing. Corresponding to this particular one, there is another fringe spacing. When these fringe they are overlapping on each other, it will give the appearance of as if a dotty contrast, but we should remember that this is not an atomic contrast. This is only just a spacing between the lattice planes is what is being given, nothing else beyond that. Okay. In this particular case, we are just showing a case where in silicon, okay, this is the sort of an aperture which is used to form the image. Okay. We look at the picture how it looks like. Okay. This is that aperture, and if you look here, this is the high resolution picture, which has, that is the lattice fringe, crisscrossing of lattice fringes in various directions. This gives a contrast which looks like an atomic contrast. Okay. If you look at the separation between these two, this essentially corresponds to the spacing is 0.13 nanometer in silicon and the beam direction is 110. We have used only 200 reflections, 220 reflection, 111 type reflection, okay, 113 bar reflection. These are all the reflections which has been used to give rise to the overlapping of the interference of the fringes, giving rise to this sort of a contrast. In this, if we look at it, the separation between them corresponds to actually D004. Okay. That is what essentially the plane D004 planes. But if you look at the diffraction spots which has been used to cause interference, we have not used D004, only D002. Okay. Then how does this D004 it appears? Okay. This sort of as if from this one point which becomes very clear is that what we are essentially seeing it here, okay, truly does not represent the lattice fringes. Okay. This arises because a fringes corresponding to 1 bar 3, okay, and corresponding to another 1 bar 3, this one, these ones, if we join them together, okay, if they interfere, that will correspond to 004. That is how we are getting it. Actually, if we look at it, we have not used, okay, diffractions pattern corresponding to 004, but then we should not get fringes corresponding to that. Okay. This is one thing which we should keep it in mind in all these images. And another is that it only gives the diffraction plane spacing, and which, because if you wanted to know the atomic structure, we should know which positions are being occupied by atoms on different planes. That information does not come from this interference fringe contrast. Okay. Here I had just shown some examples of high resolution images which has been taken on different samples, where one would look at that interface between two phases. One, there are grain boundaries which could be thin faceted grain boundaries, and these are all some twin related structures because these two regions are twin related. Okay. In this one, indium arsenic antimony, here if we look at it, the contrast looks almost the same, but there is a distortion of the contrast which we can see. As we mentioned, there is a slight shift which has happened as we mentioned earlier. Okay. This region corresponds to where some dislocations are present, interfacial dislocations are present, and when the interfacial dislocations are present, atoms are displaced a little bit. So, this gives rise to a variation in S, which gives rise to small shift in the fringe spacing here. Okay. So, what are the conclusions which we could make out from what we have covered so far? One, aperture we place it around few beams, okay, and form image using them. The fringe spacing is another, is related to a separation between the diffraction spots. That is what the expression clearly shows. Intensity, but what we have seen it is that we get separations which are not revealed by the separation between the diffraction spots. This could also be explained because this could arise due to interference between some other spots which could generate this sort of a fringe contrast. Intensity depends upon the amplitude of the interfering waves. Okay. So, from this what all information which we can have, lattice fringes are not direct images of the structure. Okay. Information on the lattice spacing and orientation is, we can get it. Okay. So, to get actual information, we should do a simulation of the images, but most of the time you will see in the literature this information which is available from the lattice fringe images are interpreted using simulation. This is only a very qualitative way in which one can interpret it. One has to be very careful because sometimes it can lead to misleading interpretation of the results. Okay. So, it is always better to do image simulation to get correct interpretation of the structure. Okay. These are some other few pictures which are taken from, one is from a high resolution electron microscopy pictures which are taken from a gamma titanium alloy, where after heat treatment it has phase separated into two phases, gamma TAAL, okay, and alpha 2 phase which is HCP. Okay. The interface between these phases, you can see the ledges which could be seen. Okay, these sort of ledges, these are all the ones in a plane interface. If it has to grow, unless some ledges are there, it is very difficult for them to go, which these aspects you might have studied in phase transformation, and using high resolution microscopy we can get direct evidence for it. Okay. And then here is even in a sample which is an amorphous sample, rapidly solidified glass. Okay. When one does a high resolution image, I don't know whether you are able to see it, at different regions one can see some lattice fringes could be seen. So, the regions where we are able to see lattice fringes, these are all the regions where it has transformed from amorphous to crystalline region. So, this had been used to find out the size of the nuclei and the number density of the nuclei. Okay. Like this you can think of how to use it to get as much information as possible, okay, in the study of phase transformation. Okay. So far what we have considered is, we have considered two beams and interference of the two diffracted beams, that is either could be a transmitted and a diffracted, or between two diffracted beams also we can use it to form images. Okay. Now let us look at this sort of situation arises in many other cases, which is called as a Moiré fringe pattern. I have talked about Moiré fringe contrast earlier. In this context, why I wanted to introduce it is that this is also arises because of interference between two diffracted spots. Okay. And as I mentioned earlier, it is a bead pattern. Okay. Here suppose we have two crystals are there, one sitting on top of the other with slightly different lattice parameter. Here the lattice parameter is small, okay, and in this case the lattice parameter is slightly large. Okay. The beam direction remains that same. Okay. When the beam is passing through it, okay, as the beam passes through it, we find that there suddenly, okay, the lattice parameter has changed. Because of this will give rise to some diffraction pattern, and this pattern also will give rise to diffraction pattern. This will happen corresponding to, like we assume that this is the one which corresponds to diffraction pattern which is arising from the one which is a larger one. Okay. The other one, what it will happen is that it will give rise to a diffraction pattern So, this is the sort of a diffraction pattern which get it corresponding to top and the bottom. Okay. If we put an aperture around, say around these two spots, and then just like what we have talked about the phase contrast microscopy theory, okay, they will give rise to a fringe pattern, the bead pattern. Okay. These are called translational Moiré pattern, and what is going to be the spacing, that is we know that the spacing between them should be equal to the Moiré fringe pattern equals to, it should be equal to modulus of GM. That is what essentially is being given. Okay. And since this is the direction from here to here, the fringe spacing should always be perpendicular to it. This is the way a fringe spacing will appear. Suppose I choose this particular two spots to form the image. Now what is going to happen is that the fringe spacing will appear like this, perpendicular to it. That means that depending upon the type of vectors which we use it, the fringe spacing is going to change. That is the bead pattern which we get, it is going to change, but as far as the crystal is concerned, they are in the same orientation. That is what one should see. Similarly, this is where it is one crystal and another crystal is parallel. It can so happen that the crystal, one crystal could be rotated with respect to another crystal slightly. This will give rise to a rotational Moiré fringes. Okay, there also these expressions we have derived and look at it. Now we can see that this is for the translational one and the rotational one. Okay. This is the sort of a diffraction pattern which we will be seeing it. That is what I had shown, but I will not, you can see that more spots could be coming. This is because each of the beam can act as a another primary beam for diffraction, because the strong diffraction takes place in the sample for electron beam, and that gives rise to this sort of extra spots. What is essentially important is that this gives rise to, this is the sort of a fringe pattern, but if we measure this separation between these Moiré fringes, we can get information about the difference in the lattice parameter between the various phases. Okay. That is essentially what is being given here. There are many applications are there. One of the first application which was is that this Moiré fringe pattern has been used to find out how the in the case of an edge dislocation, when there is an extra plane is going to be there, this gives rise to that appearance which is similar to the planes. This, if you remember, generally when we draw for an edge dislocation, this is how, this is the slip plane, this is the extra plane which is there, the upper half above the slip plane, and this sort of a direct contrast of the edge dislocation image could be obtained using Moiré fringe contrast. Okay. There are many other applications are there which I am not going into the detail, okay, that you can see in most of the standard textbooks and look at it. I can give you some assignments also and suggest some books which you can read it. Okay. Similar to this, another type of a contrast which occurs in a microscope, okay, it is a phase contrast which is called as a Fresnel diffraction. Okay. We know that in optical microscopy we have studied that when aperture is there, okay, as the size of the aperture is of the same order as the wavelength of the radiation, then when we look at that image, in the image we get one central region, okay, and this region is followed by rings. Okay. Essentially these appear because of what we call as the Huygens principle. Huygens principle, what it says is that at every point as the electromagnetic radiation propagates, each point acts as a source for a spherical radiation. The waves which are from a particular, if it is a plane wave, if we consider from various points, we have plane waves which will be emitted like this. These waves will be interfering together, and where the crust reaches, this is the next one. From here again this will be acting, emanating waves. This is the wave propagates. Here what is happening is that we have a wave which is there. From this region it is going to come like this, okay, scattered radiation, spherical wave, and then this direction, their interference is what it will give rise to a fringe contrast. That is what the fringe contrast which we are essentially seeing it. The same type of a fringe contrast can arise because in a microscope from one defect region, that is from a grain boundary or a magnetic domains, which we go from one region to another region, sudden change of potential is there going to take place. This change of potential can give rise to scattering of the electron beam in different directions, and they will give rise to interference pattern. So, here what is we are considering, one simple experiment with which we can do it is, if we take a small wire, okay, if a glass which is coated with metal, and if we take it and apply a voltage, the beam which is coming in this direction, this will be attracted towards and it will travel in this direction, this will be traveling towards this direction, as if now it looks like this beam is coming in this from this source, the beam is coming from this source, okay. These two interfere and the interference fringe pattern will look like this particular one. This is what we call it the Fresnel fringe spacing, and the separation between them depends upon the wavelength of the radiation, angle through which they are scattered, okay. Then from this object to the screen distance, as well as from the object to the source distance. These are all the factors which it depends on. Okay. What is the application in ferromagnetic materials or magnetic materials, okay, or in ferroelectric materials, okay. The boundaries which are there between these various domains, there sudden change of electric or magnetic field will take place. This will scatter the beam in different directions, and this will give rise to an interference which will give rise to this sort of a fringe pattern. Okay. This way we can identify the various types of boundaries which are present on the sample. Another application which we can think of is that, suppose in a sample which is irradiated, that contains some helium gas bubble is going to be there. So, the helium gas bubble is nothing but, in a sample if we consider, it is something similar to a vacuum. So, the potential is 0, on the other side there is going to be a potential, okay, where the sample is there. If we do a little bit of under focusing, then what we can see is that some Fresnel fringes will be formed around this, and using these fringes we can identify the defects, that is in this particular case the gas bubbles which are voids which are going to be there, okay, and we can count them to find out what is the void density, void size, all this information has been obtained. The theory of it you can see in the relevant papers which are published in the literature. Similarly, if a low angle boundary is there, which periodic arrangement of dislocations which are going to be there in that boundary, then also since there is a sudden change in potential is going to be there, this will give rise to a sort of Fresnel fringe contrast, and this fringe contrast also will vary depending upon what sort of focusing which we use, at zero focus condition or under focus or over focus. These are all the various ways in which you can do. This is another where an edged the grain boundary itself in a sample which has been seen an edge on orientation, and here we can see that depending upon the there is a bright line and dark line could be seen. This sort of contrast is arising again because of the Fresnel fringe contrast. So, you can understand that this Fresnel fringe contrast could be used to get a lot of information about the different type of boundary, but to understand them completely why they arise and what sort of boundary it is. We have to do some computer simulations, which is very much necessary. Okay. That part of it is beyond the scope of this lecture, but basic image simulation which is required for high resolution I will be talking about in the later classes. Okay. So, what we have done so far, we have discussed a phase contrast image formation in an electron microscope when the lens aberrations are 0. But real microscopes contain the lenses are not aberration free, they do contain aberration. Okay. If aberration is going to be there, how this aberration is going to affect the image contrast, okay. How some of these aberrations which are present is used to still get high resolution images. That is what we will be discussing it in the next lecture. Okay. So, essentially in this lecture we have considered an ideal lens, okay, where for a point object we are able to form a point image. In such a case, how we can get a simple fringe contrast which can be obtained, how these fringe contrasts could be related to the lattice spacing. Okay. I will stop here now. Thank you.